35 number 6. Waiting for it to turn on the machine. Okay, so all I wanted to say about this one, okay, again, make sure that what you're sitting with in front of you are not the outlines from the back. Those are trig. Yours are on that table over there. All right, so for this particular problem, let me focus it. Anyway, what we were talking about quite a bit before you left was what is the shape of anything that has the variable down at the bottom. So what we were figuring out is that that these graphs have asymptotes, and if there's only one asymptote, you'll have a hyperbolic wing here and a hyperbolic wing there. It could be here and here, or it could be there and there. The minute that there's two asymptotes drawn, and you might want to put this somewhere on your outline, the minute that you're into this situation here, let's say there's an asymptote here and an asymptote here. This is just the y and the x-axis. Basically, the shapes that are going to happen, not basically, exactly, the shapes that are going to happen in the middle will either be a parabola, and that parabola, I'm talking about this middle section, because you can't do a hyperbolic wing because it'll cut through the asymptote. So we don't have that option in the middle. So you will either have in the middle either an upward or a downward parabola. Your other option is the cubic, C-U-B-I-C, the cubic shape, which is the one that goes like this. It could either go like that. So you might have a situation where it goes like this, or you might have a situation where it goes the other way. Those are your two options in the middle. However, on the ends, you have the hyperbolic wings, and they could both be like this. They might be both up in the, in this region right here. You might have one there and one there. Sometimes they're catty-corny. Sometimes they're both above the horizontal asymptote. Sometimes they're both below. So look for the wings to occur on the end, but in the middle, if you come across a problem like that, you'll either have an upward or a downward parabola or a cubic shape. That's in the middle. Okay, so going back to this graph, if you were to put that into your calculator, is just what we call the parent graph. No shifts, no nothing. Just bare bones hyperbolic wings. This would serve as the horizontal asymptote, the x-axis. This right here would serve as the vertical asymptote, and there would be your two wings wedged in between the two asymptotes. So what they're trying to get you to understand here is that no matter what shape I teach you, these just happen to be what's called rational fraction shape. These are rational expressions where the variable's in the bottom, so you get these wings. But they can still be shifted. Just like you can take a parabola and you can shift it up or down or left or right, you do the same things here. But you know where you're going to shift them from? The asymptotes. So let's see if you recognize these shifts. These were back in chapter 2, but then they kept coming up, especially in this chapter. See that right there? Free loose 7, not attached to the x. It's all by itself doing its own thing, hanging out at the back of the function. What kind of shift is that? Vertical. It's vertical, right? Now, think about the asymptotes that you have. You got your graph. Your graphs, your little wings, your hyperbolic wings, they hang around by the asymptotes, and they let the asymptotes control them, basically. See the asymptote that goes like this, the horizontal one? You got one wing shift perched above it and one hovering underneath it. And they have a magnetic attraction to that asymptote. So if you take that horizontal asymptote and you push it up, it makes the wings go up also. The one wing that is above it will go up right with it, and the one wing that's below it will also go up. So if you move that horizontal shelf that those two wings kind of are magnetically attracted to, they're going to go right with it. If you take the vertical asymptote, the one that's like this, where there's a wing here and there's a wing here, and you push it this way, both of the wings are going to go that way. They stay stuck to the asymptotes. They never touch them, but they get ever so close to them. They have an attraction to those asymptotes, and they travel with the asymptotes. So that being the case, let's answer this question without getting all nuts about it and put it in the calculator. I would memorize this shape. This is the basic shape of anything with a variable at the bottom. Now, I have taught you to graph things that have asymptotes in different places, more complicated than what you're seeing there. However, with respect to this question, if this is a vertical shift, and you might want to label that vertical shift of 7, you can expect an asymptote that's typically at the x-axis to push up 7 spaces. Do you see any graph that's like that? Because maybe just by knowing vertical shift, you might be able to answer the question. Which one of these graphs has hyperbolic wings, even though they're not showing you the entire wing, but it has been pushed up 7 units in the air? B and D? Okay, so maybe it is B and D. It looks to me like this is, yeah, that is shifted up. You can see that horizontal asymptote? It used to be here, and now it's 7 units up there. You see it going right through 7? And then let's see, isn't D doing the same thing? Okay, so we're going to choose between B and D. Now we also want, I didn't think they would make it that easy for you. Now we also want to look at the horizontal shift. What kind of horizontal shift is that? Positive 2 or negative 2? Negative 2. All horizontal shifts, try to get this by the time you leave this class, because you'll be doing it all the time if you go on. They always, before you break the number apart from the x, you switch the number. Okay, so write that in your notes, and let's pick the answer. You're going to pick between B and D now. This was a vertical shift of, it went up, because vertical shift behaves exactly as the sign you're looking at. Whereas these right here, the horizontal shift, they behave the opposite. So you're really trying to enact a negative 2 horizontal shift. Now the only thing that you can move horizontally is that vertical asymptote, the wall that comes down like this. You're going to pick that wall up and you're going to move it this way. Not to positive 2, to negative 2. So what graph looks like it has slid over 2 units? B. This one has slid over. See that vertical asymptote right there? It used to be pasted to the y-axis, but it has shifted 2 to the right. You're not supposed to be doing that. This says that you should have a horizontal shift of 2 to the left. Even write that down if you need to, if you don't understand what negative 2 means. That you should have shifted 2 to the left. They're saying it with a number. They're saying it in words. Shifted to left. I said this both ways also. I said it went up. It's the same thing as having a vertical shift of positive 7. Okay, so this one has to be the answer right there. It's 7 units higher than it usually is, and it's 2 units to the left of where it usually is. Because usually these things are down here. This would be below, and they would be on either side of the y-axis. All right, so 8 I had already done. That's it for that section. Let's go to 3.6. 3.6, I don't know how involved we're going to get with that, but it's pretty easy. Here it is. I'm not doing problem after problem after problem because it's just the same thing over and over again. I just happen to choose, like I always do, a lot of problems. Okay, do you understand that what you are seeing here in the problems that you can see, that they're all second degree? Everything's second degree. Now, you guys are probably experts at solving first degree inequalities, but have probably more than likely forgotten how to deal with second degree. So second degree, what you do is you pretend as though it's an equation, just temporarily. Okay, this will be step 1, and we're going to find what's called finding the cut points. Now, they've been nice enough to factor this for you, because you know what you're actually going to find, and what I'm calling cut points, are actually the solutions if it was an equation. In the end, anything that has a less than or a greater than, you will be shading the infinite solutions that there are for the problem. However, you can't get to that just right off the bat. You need to go through these steps. So right now we're going to pretend as though it's an equation. If this were an equation, it would just have two solutions that are afforded to us by these factors. These solutions are what we now call cut points because they are going to cut up our number line into several areas. So I don't know if you're actually still showing yourself, but what would this factor give you as a solution? In other words, what I'm saying is if I made a little baby equation out of that, x minus 2 equal to 0, what would be the answer to it? 2. Okay, I don't care if you show that work or not. This factor gives this solution. What I am now finding are the solutions to the equations, or they can be called the cut points of the inequality. This one would give you negative 6. Okay, step 2, take your cut points and place them on a number line. These cut points will cut up the number line into several sections. So we're going to put negative 6 would be for, you can put the 0 on here if you want to, but I like to not put any more numbers other than the cut points because it can potentially confuse you as to how many areas you got to test. You have 3 areas here. If you have 2 cut points, you got 3 areas. You need to figure out which of the areas, and there might be more than one, which of the areas has the solutions. The solutions are many. They're infinite. Okay, all less than and greater than have infinite solutions. So what I can tell you to cut down on your work is this. You can get away with just testing one area because what happens with second degree is that if one area works, the next one doesn't, the next one does, the next one doesn't. They alternate. What works and what doesn't work alternates. So you could basically go into whichever area you thought would be the easiest to check. I like to go where the 0 is because I find 0 extremely easy to plug in and to do the calculation in my head. So you're going to see me just, that's my deal. I always go to where the 0 is. I test that one area, and by testing that one area, I know what's happening in all 3 areas. So I'm going to go right in here. I'm going to announce to my teacher what I'm checking. I am testing, pick any number that's in here. I like 0. By you testing one number that's in that region that I'm sitting in the middle, you're really testing all the numbers in that region. Just pick one that represents it. So here I come over here. Here's me actually testing it. You have to test your chosen number in the original inequality. Okay, so my original inequality was something minus 2. You're going to put the test point in there. Something plus 6. And it should be less than 0. If the numbers in the middle are truly solutions, and if they are, I'll shade them, then I should get a true statement here. Okay, go put your tester point. I chose to test 0. That means I'm going negative 2, because 0 take away 2 is negative 2, times 6. I get a negative 12. What do you think about that statement right there? Do you think negatives, aren't all negatives less than 0? Okay, so that is a true statement. And anywhere that you're going to get a true statement, everything in that region is a solution. Now, remember I was telling you they alternate? Everything in the middle works. That means nothing works here, nothing works here. And you can put a yes if you want to put a yes instead of true. True means yes, everything in that area works. So yes, everything in here works. No, the yeses and the nos, it's as simple as I can break it down. The yeses and the nos alternate. So nothing in there works. And you could try it. You could try any number you want that's over here, like a negative 7 or negative 8 or even the decimals, and you could plug it in and you would get a false statement. You could try any number in here just to satisfy your curiosity. You could go plug it in and it also wouldn't work. The only numbers that are going to work are right in here. Then you have to give me the answer in interval notation. So you're going to graph it, and you're going to give me the answer in interval notation. Do you see that this little inequality did not have a little equal sign? So nice, soft parentheses. Everything in here works. Bring the answer down here. Give me your answer in interval notation. Okay, everything from -6 to 2 worked. That's a picture of it. Okay, let's go again. This time, we'll do more. Really, what I got to work with you here, I don't think you find anything that I just said challenging. I guarantee you're not going to find that challenging. What you guys are always challenged with, for some reason, is the factoring. Because if you can't factor, you can't get to this stuff. So let's practice the factoring. All right, so let's see. If we could just get this thing factored, we'd be right back where we were with the last problem. This is a greater than. We know x times x is x squared. And remember, when it's 3 terms like this, second degree, first degree, 0 degree, you're looking for, this is called guess and check, 2 numbers that are equal to the last number. But when you add those 2 numbers, you get the middle number. What can you think of for that? Yeah, -6 and -3. That works. See? All right, so negatives, doesn't matter which one you put first, and -3. So if you can get past your factoring dilemma, you're going to probably do very well with this section. Okay, here is my number line. The solution for this, if I was treating it as an equation, would be x equal to 6, and the other one would be x equal to 3. Cut up your number line with those 2 numbers. You can put the 0 on there if you want to. Okay, let me stop before I finish the problem. I'm about to finish it. Ask your questions if you have one. Don't stay quiet. What do you want to ask, if anything? Nobody? Okay. Oh, yeah, I wrote it twice. Thank you. Don't be afraid to talk. All right, thank you. So 3 and 6, and I got the 3 and the 6 on there, right? And I'm just going to go and check whichever area I feel like checking. Now, I know that if I check over here, well, what area do you think the 0 is in? I don't know if you like checking zeros. I do, but you don't have to follow what I'm doing. You could plug gigantic numbers in there if that's what you're into. Where would the 0 be? Because not only do you have, if there's a number that you have in mind that you really like to check, you got to know what area it came from. The first region, second region, or third region. Where is it? First one. Okay, so I am testing this area right now. I'm testing 0. Please check whatever you want. I'm going to come over here and check it. I'm going to check this is called a test point. These numbers are called cut points. All right, so let's see. Go in the original. You're supposed to check it in the original because what if you made a mistake when you factored? Then checking is not going to do you any good. So this went x squared minus 9x. I'm copying the problem in the original form. Okay, we're plugging in. See how easy that is? Because it gets rid of that. It gets rid of that. So essentially, all you have left is the 18. Is 18 greater than 0? Yes. So put a yes here. That means this would be a no, and this would be a yes. The yeses and the nos alternate. Now give the final answer. You're going to read now you got it's a more complicated answer, right? Because you got 2 yeses. So you're not just talking about one area, you're going to have to talk about both areas. And you're going to join the answers with the or symbol. Okay, so you're going to say anything over here works, bless you, or anything over here works. Come in from the left. Come in from the left side. The numbers that are all the way out here, because you know that number line goes on, right? So the numbers that are out here are called negative infinity. You are going all the way up to 3 with a soft parenthesis. Not a hard bracket because there's no equal sign in this problem. See? No equal sign. So you're going to talk about all the numbers that are out here. Those are called negative infinity all the way up to 3. I got to move down here. I didn't give myself enough room. Hold on. Let me get some paper. Okay, so this left tail end is negative infinity all the way to 3, not including 3. Infinities always have that. Or you can also find answers from here to positive infinity. So 6 to infinity. What do you think? Is that easy? Pretty easy. Okay, again, the factoring will be your problem. Let's go to the one that I think you find most challenging, which is guess and check, but with a number in front. Let's practice that one, because that's the one that seems to mess students up. So forget number 3. It's more of the same thing. Let's go to one that's like this, a little bit harder for you. All right, so for this one, you know how when I was doing guess and check in the last one, I started by looking for a product that was equal to the last number? Well, you can't do that for this one. You have to incorporate the last number as well as this. In fact, you multiply those two things first, and instead of just taking that negative 6 and dumping it right there like you do with the easier one that I just did, it's 3 times negative 6, negative 18. This is A times C value. So you're looking for a product that's equal to negative 18, but from here on, for this step, it's the same. But these two numbers that you're going to use here again should add up to the middle term. Okay, so wouldn't that be 18 times negative 1? Okay, so 18 negative 1, and then make sure that when you add those two numbers that you think are going to work, that they check out to make sure that that comes out right also. So this is the B term. It's the one in the middle. Okay, now here's where it completely is different than regular guess and check. Okay, it's the same emphasis. It starts off slightly different, but now we're going to break off into grouping. It's the easiest way I can think of to get you to be able to do this kind of factoring. So you write the first term as is. You're not going to do that anymore. We're going to use these to rewrite that 17x. So 18x minus 1x. Here's your 17, and then there was a negative 6. Okay, we're still trying to factor it. Almost there. Now we can do factor by grouping. We could take a 3x out of these two. Forget those two right now. Factor by grouping, you treat two of them at a time. So it's 3x times x is x squared. 3x times 6, 18x. Come to the back. Notice that when you take out negative 1 and put a parenthesis, you end up with this same thing, x plus 6. Then to finish the factoring here, what this has in common with this is x plus 6. And then the other parenthesis, 3x minus 1. That's challenging for most people. That's the form. There's 6 different ways to factor. That's the one that students usually have the harder time with, like they just can't remember. So now take this and go over here. And we're going to write this in factored form. So pretend as though this is the equation. All of these factors. I'm thinking you can do this one in your head, but I don't know about that one. So if you can't do them in your head, like you know that the one that makes this 0 is a negative 6. And if you can't do that one in your head, then just come off to the side and go like that. But it is 1/3. You would move the 1 over here, which would leave you with 3x, divide by 3, and yes, it's 1/3. Okay, again, you have 3 sections because you have 2 cut points. The only time you're not going to have 2 cut points is when you factor. See if you can wrap your head around this. What if you factor and it comes out x plus 7, x plus 7? They both come out the same because sometimes that happens, right? Then you'll just have 1 cut point and 2 areas. But if you have 2 cut points, 2 different numbers, which will happen in 99% of them, then you'll have 3 areas. Okay, so I'm going to test right in here my favorite, testing 0. Okay, so let's see. What was my original? My original problem was 3x squared plus 17x minus 6. I'm looking for that to be less than 0. Make this smaller, sorry. I'm testing 0 because I know it gets rid of almost everything so that you don't have to touch your calculator. So gone, gone. Only a -6 is left. What do you think? Yes or no? Is that true? That's true. So you're going to put a yes in the region where you just got this test value. So this is yes, therefore this is no, therefore this is no. So all you have to talk about in your final answer are the areas that have yes. Okay, so you're going to go right there in the middle, -6, comma, 1/3. Now, was there any equal signs in this problem? No. Okay, that's your answer. Let me see if any of these problems have any value, because I think I just kept giving you the same ones over and over again. All right, you ready to jump to one that has 3 different cut points? Let's jump to number 8. I'm going to do 6, 8. No, I think I'm going to do 8 and 9. I'm going to do 8 and 9. All right, so I better do 6 too. Okay, so here's 6. Sorry. So 6, you write it on your paper. I don't know, I just feel like you're going to mess up if I don't do a few more. Okay. Anyway, you know that when you factor, you got to get it on the side. If I was you, I would try to get it so that the x squared term is positive. Therefore, I'll move everything over here because it'll make the factoring easier. So I'm going to bring this over here, and I'm also going to bring this over here. Keep in mind that everything changes signs as you go from one side to the next. So it's going to be 3 squared, 3x squared. It's going to be positive 7x was already on the left. The 6 is going to come over here as a -6, just like this came over as a positive. So -6. That symbol is still the way it was, but now there's nothing on the right-hand side. So make sure, that's why I gave you this one, that you would remember to get everything on one side. Treat it as an equation. Just for right now, you're going to treat it temporarily as an equation and try your skills at factoring. Again, I just gave you one like this. Let's try it again. This is the one that students are the worst at. You start by trying to find a product that's equal to your A times C value. That's that times that. But these numbers that you claim work here, there's a lot of numbers that work there, but only one pair will also accomplish this. What are they? Yeah, all it's going to be is about you knowing some real simple times tables. That's all. But if you can't remember that you need to use A times C, you're going to blow the whole thing. So you got to memorize the procedure. Okay, so this is 9 and 2. To make this happen right here, to get a positive number, the bigger number has to be positive while the smaller one's negative. That'll make that and that work. As soon as you find the 2 numbers, that will accomplish both that step and that step. You're going to rewrite the problem, stretching it out into 4 terms. So this will be 3x squared. Instead of the 7x, you're going to do 9x minus 2x. Okay, there's your middle term right there. And then minus 6. Now factor by grouping. Take out 3x. This will be x plus 3. Take out -2. That'll leave you with x plus 3. And then look at this as 2 terms now. This will be one term. This is the other term. They both have x plus 3 in them. Where my pencils go? Okay, so that'll be 3x minus 2. So the cut points are x equal to -3, And for this one, again, I don't know if you could do that in your head, so I'll just show it to you. This would come over here. This would be 3x equal to 2. Divide by 3, so x is equal to 2/3. That's your other cut point. Okay, toss the cut points on a number line. And test one of the regions. I'm going to test right up in here. As you're passing between a negative and a positive, that's always where you'll find the 0. All right, so let's see. What was my original? 3x squared plus 7x minus 6, so 3. Okay, now I'm testing the 0. 3x squared plus 7x minus 6 equal, oh wait, now I need the original. Do it in the original, which was less than or equal to 0. So I put 0, 0, gone, gone. Only the negative 6 is left. All negatives are less than 0. So wherever I got the 0 from, that would be a big yes, a no on both of the ends. Okay, so only this area right in here is the final solution. So final solution, negative 3 to 2/3. You always go at the answer coming from left to right, smaller numbers first. Now let's see. What do I have to put around the numbers this time? Brackets, okay? I'm going to put a bracket because of the little piece of equal sign that was in the original problem. See it right there? Okay, so we're going to go bracket, bracket, and you would even put those brackets in the picture. Okay, let's go to, I don't know that I need to do that, but I would do number 8, but I think I can handle number 9 if I do not, look at these two problems. Do you see how there's 3 different parentheses in number 8? I'm going to get that, let me see, I'm going to get that anyway for number 9. So if I do number 9, I'm going to be showing you how to do number 8. I'll just do number 9. Okay, let's go to number 9. See what happens when there's 3 different cut points. All right, what kind of factoring do you think I should be doing in this particular problem? Grouping, because it's 4 terms. Okay, so let's just take the first 2 terms. These both have an x squared. You always put 1 parenthesis when you're taking out a GCF. That's what that is. So x squared times x gives you back the x cubed. X squared times negative 5. There's my negative 5. Gives you back that term. You're done with the front 2. Now go to the back 2. It's negative 25x plus 125. So I don't know whether to take out a negative 25. I mean, definitely 25 goes into both of those. You got to fiddle around with the negative to see it to make this happen. So let's see. If I was to take out negative 25, I think that's going to work because that times positive x. I wanted this to be a positive x because that's a positive x. And then negative 25 times, how many times it goes in there? 5 times. So yeah, negative 5. So negative 5, see, this times this is negative 25x, and that times that is positive 125. So it's all factored, almost. Now look at this as 2 terms. This is 1 term. This is the second term. These both have x minus 5. And then what goes in the back parenthesis are these things that you pulled out. But do you see that this problem, unlike any of the rest I've done, that all of a sudden it's 3rd degree? So you have to cut points. 3 solutions. Cut points are solutions. So do you remember how to break this down? This one's not called guess and check. It's just knowing, this is just the difference of squares. All you do is take a square root. So you're just going to go 2 parentheses so that you can continue breaking this down. You take the square root of the front term, that's this guy, and put it here and here. You take the square root of the back term, put it in the back of each one, and then alternate the signs. And in doing that, you have 3 different factors, and 3 different cut points. This will give you the cut point x equal to 5. This will give you the cut point x equal to -5. And this will give you the cut point x equal to 5 again. All right, so let's see here. All right, since 2 of them matched, we're only going to have 3 areas. So it's -5 from there. Both of these came out to be +5. And now continue testing. Yeah. Yeah. You would get x equals plus or minus 5. Yeah, you can do it. It's not going to change what's going to happen right now. You're still going to end up with 2 cut points. Even if you would have done that, you would have gotten plus or minus 5. We already knew about the -5, or I mean the +5, because we already got it in another one. And you still would have had 2 numbers here. But yes, you could do that if you want. Okay, so now we got 3 areas here. This is where the 0 is, so get right in there. Go into the original problem, which was, here it is right here, x cubed. Now you're going to, I don't know, you might get into where you're like doing this part in your head. But I would like you to at least show me this right here. I don't care so much if you copy this whole thing, but this next step, I would like you to show me so that you could, like, I could see that you know what you're doing. You're going to put a 0 here, here, and here. Now I realize that makes all of those go away. That leaves you with +125. What do you think about that? Is that true? No, that's not true. So there's a no there, and therefore what do you need to write here on the ends? Yes, that those numbers do work. So here you go again, trying to talk about 2 different regions that work. You're going to come at the answers from left to right. So let's see, did we have an equal sign in this problem? No. So we're going to say everything out here works and everything out here works. So this is called coming in from -infinity all the way to 5 or -5. Or there's also answers out in this region, 5 to +infinity. Okay, let's jump to the end of the section. Look at these problems 10 and 11. Okay, so use the graph of the polynomial function to solve the inequality. Type your answer. All right. The solution says this is okay. Okay, so let me show you what you're looking at. They kind of did the work for you, part of it. They did part of the work for you via the graph. What do you think this graph tells you? I don't want to spoon feed it to you. I'd rather you discover it yourself. What do you think the graph is giving you that we've been working so hard to get ourselves? But now it's just being handed to you. Not the entire answer, but it's being handed to you part of what we were working so hard to get. What do you think you're supposed to be getting off the graph? The cut points. Okay, because remember, didn't you hear me say that cut points were solutions? And have you heard me say in the past that solutions are the same thing as x-intercepts? When you're talking graphs, it's where the graph hits the x-axis. Those are the same things as solutions. And so where is this really hitting? At 2/5, so they say right here. And then where else is it hitting? -5 and then, yeah. Is this 5? Yeah. So, all right, let's write the cut points down. So from the graph, you are being given negative, what is this, -5? Okay, so -5, blah, 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 blah. We're also being given 2/5. And I got something even better for you here. I think we could do this without the number line, but let's go ahead and write the cut point. So let's do, so we said -2/5 was a cut point, and we also said +1 was a cut point. We're going to do this answer without the yes, no stuff. Okay, couldn't I take this equation and rewrite it like this, or this inequality, because it's really an inequality? I could leave the cubed term there. I could leave the squared term there. I could bring the 17x over there, and I could bring the -10 over there, leaving the greater than or equal than sign and a 0. Let me tell you how to read the answers for this graph, because I want you to be able to do either kind of problem. So what I just did here, this is still the same inequality as that. This is a picture of the inequality. You see the 0 that I have right here, the 0 mark? That is represented by the x-axis. So when you are looking for the graph that represents this, which you're staring at already, the graph that represents this, you want all numbers, x values on the graph that are greater than the 0 value, or in other words, the x-axis. That's the same thing as saying that you want to get your eyes to zero in on the portion that's above the x-axis and then talk about the x values that go with it. So I'm going to help you do that. You want the portion, and this is because of the greater than. Greater than means give me the portion of the graph above the x-axis. If I had put a less than symbol in there, you would want the portion of the graph underneath the x-axis. So this is, you're looking for the portion that's above because of the greater than or equal than symbol. Now, do you see that that's all this? Everybody see what I just colored in? I do not care about this little tail, which, by the way, goes out like that. It looks like it goes straight down, but it really flares out. I don't care about this piece. Those are portions of the graph that are less than, you better write this on your graph. This is called the 0 line. That's why I set it equal to 0, or made it greater than or equal to 0. So this right here is called the 0 line. So when you want all the points on this graph that are greater than the 0 line, that's like saying you want the portion that's above. However, now let's give the answer. These, what you're seeing right here, are all the points that are above. I want you now to just talk about the x's. What are the x's that are associated with the above portions? What is the x value? Let's dig in right here. What is the x value associated with this point right here on the x-axis? What did you tell me that value was? -5, right? So we're going to begin this above portion. We're going to talk about that entire above portion in the form of an interval. See, this takes the place of all that cut point stuff we did and all the testing that we did. We're not doing any of that because visually you can just see the answer. We're going to go that the x value here is -5. This has an x value. This has an x value. This has all these points that are on the graph. They all have an x value if you drop down to the x-axis. But can you understand this? What is the x value there? What did you tell me the x value was there? Well, they told you what it was, right? They said it was -2/5. So do you think it would be safe to say that the x values that go with this are between -5 and -2/5? Isn't every single point on this hump right here associated with an x value between -5 and -2/5, taking the place of all the cut point work that we did? Okay, we're also going to talk about this little tail, but let's first give the x values that go with this. It's anything from -5 to -2/5, and they gave me both of those values. What do you think? Should I put parentheses or brackets around these numbers? Brackets, and that's because of the little equal sign. So anything from here to here is good, or don't we have another above portion? And that would be this piece right here. It's above the 0 line. You just have to know that The 0 line really means the x-axis. So look at these, the x value that's right here, where the above portion starts, isn't it at 1? And then this would be bigger than 1, bigger than 1, bigger than 1. By the way, this flares out. You should probably put like a little arrow there so you know that this thing doesn't go straight up. It actually flares out, out, out that way. So you're going to say that this portion that's above starts at positive 1 and goes to negative infinity as far as x values go. Oops, positive. I meant to say positive. See, that's when you don't have to do the cut point at all. If they're already giving you a beautiful graph and you can see the dig-in points, the x-intercepts, you're going to be you're given the answer. You just have to know how to read it. Okay, one more. All right, so this says solve the inequality using a graphing utility. Choose the correct answer below. All right, so get your graphing calculator out. Everybody get your graphing calculator out and see how would you be able to do this on a test. What we're going to do is we're going to produce the graph ourselves. And you need to get the window nice so you can see where the dig-in points are, where the x-intercepts are. Okay, so you see this problem that you have on your paper. I want you to temporarily pretend that it is equal to 0. You can then replace the 0 with the y. So this is what you will be this is what you're going to be entering in your calculator. Y is equal to 2x, but you have to have everything on one side, but they gave it to you like that. Go put that in your calculator. 2x squared plus 9x, and then we'll talk minus 5. Okay, so let me check my mode because I was doing stuff with another class today. Radians, we need it to be in function. Second, quit. All right, so y is equal to, get rid of that, and go put in what you have. 2x squared. Then put in plus 9x minus 5. Plus 9x minus 5. All right. Now, I don't know if this is, you know the points that are right here, the x-intercepts? You could either figure them out yourself through factoring, or you can try to go to second table. If you are going to look on, we could also find them another way. I could help you find them through second calculate if we can't find them on the table. If they are on the table, it'll have a 0 for a y coordinate. So let's see if we can find these numbers on the table. Or why don't we just do it like this? Let's go find this one right here. Go second, calculate, get up here, practice these moves, because if I give you one of these problems on the test, you're going to forget them. We haven't done them for a while. Let's see. They're called zeros. Solutions, where they dig into the x-axis, are called zeros. So go down there. See where it's blinking? You're over here by this one. So if you want to find this one first, and then we can go after this one. All right, left bound. Look where my pointer is. You want the blinker to get closer to where my pointer is, but you want it to be on the left side of where my pointer is. So let's just get closer. Remember how you move the blinking light with these sideways arrows? Get closer. As long as you're underneath the x-axis, you're on the left. Because look, the pointer is right there. This is slightly to the left. So yes, it is a left bound. Tell your calculator, yes, I've given you a left bound. Then it'll say get on the right of that x-intercept. Whoops, let me get a little closer. There. That's slightly to the right of this point, that blinker, just a hair to the right. So say, yes, I've given you a right bound. It'll say, would you like me to guess at that point? Yes, I would. Press enter again. There you go, 1/2. So one of your dig-in points is 1/2. Now let's go get the other one. Clear your plate. Go second calculate again. You got to clear the memory. Tell it to do a 0, but all over again. Now get over here. Only use the sideways arrows or you're going to hop off of the graph. Here we go. Now let's see. They want me to be on the left of this point right here. So that would be where you're on this part that flares out, then you're to the left of that point. You might want to get a little closer. Anything above the x-axis is slightly to the left of that. So say, yes, I've given you a left bound. Now it'll say get on the right. Move underneath it. You can be there if you want to, or you can get closer if you want. I'm going to just go with that. Say, yes, I've given you a right bound. I want it to guess at the answer. There we go right there. That's -5. Okay, let's bring this information back to the paper. Okay, which one does it look like? I think it looks like B also. That looks like about 1/2 right there, where it digs in. It's right before you get to the 1. And this is definitely at, right there, -5. Okay, let's give the answer now. We're going to practice one more time what I just taught you with the picture. Okay, we're not going to do the cut points ourselves. We don't need to when you have a graph. Do you see that this says that you want the graph, because the graph represents the inequality. It represents all of that. You want the graph to be greater than 0. The x-axis represents the 0 line. It represents a height of 0. So you want the portion of the graph. We decided it's this graph that's above the x-axis. We want these legs. Okay, so you're zeroing in on the legs. That's this piece and this piece. And you want to talk about the. So the first x value I'm talking about for out here is 1/2. And then what are these values? Bigger than 1/2, the x values? What do you think? Bigger or smaller? Is that positive infinity, these x values, or negative infinity? Positive infinity. That's for this tail on the right. Now let's talk about this one. This one, you got to talk about -5, and then you got to talk about how all these x values get more and more negative. So that would be negative infinity. So negative infinity all the way up to -5. There was a no equal sign there. So all of that. Okay, so you can get the answer either by hand, manually, or if somebody gives you a picture, or you want to do one. I like to just solve them with cut points, but if if they force one of these graphing problems on you, you got no choice. Okay. So that's it for 3-6. That concludes everything that you're going to be tested on. But you know I got to go on to chapter 4, right? Because on the night of the test, you have 4-2 and 4-3 that I'm supposed to teach, which wipes out the review. So there's nothing I can do about that. I don't have any kind of control over that other than I could go as far as I can tonight. Obviously, I still got an hour and 25 minutes left. So go take a little break, 5 minutes, come right back, and I'm going to kick into it. Because the more I do tonight, the less I have to do on test night. Test all of them. Still yes, no, yes, no.
Okay, so I could pick 0 then?
You can, yeah. 0 would be over here. Yeah, pick 0. Whatever you get here, this will be the opposite. This will be the opposite of that. This will be the opposite of that. The procedure doesn't matter how many areas you have. You test one.
So on 4 point, or is that going to be on that one too? Or is that just
No, it's called the chapter 3 test. Yeah, title of the test.
All right. I
Chapter 3. I never put 2 chapters on one test. You're lucky if you guys can pass 1 chapter at a time. It's the truth. That's not a cut. It's reality. What? What do you want to ask me now?
Is it possible for us to take our test before Wednesday?
Yeah.
Do you have a soccer game that day?
Of course.
Awesome.
You girls are sort of nice. I mean, I like you a little bit. My pants are falling down.
Like whatever day is easiest for you. Like,
How about Saturday?
Okay.
Just
I'll be
kidding.
here.
Wendy, can you email me though? Because So when do you want it to appear in the testing center?
Tuesday before.
Tuesday before? So we're scheduled for next Wednesday to take it so on Monday, or Monday or Sunday night, so that as soon as I come in here, I read it and run it down there for you, because I won't remember right now. Yep, no problem. So cute. Do you want to go talk to your friends? Oh, these are your friends, right? So you guys all hanging out together today.
Yeah.
What do? All come to school together? Do you ride together?
We go right from school, we'll get something to eat, and then come straight here.
Oh, nice. That's nice. I love to see you in a fun group like that. How'd you get involved? Just kidding. That's nice. Isn't it nice to study with a group? I like to buddy around. Like when I go to residency in the summer and I have to live on campus for the program I'm in.
There you go, yeah.
We have, my school has a hotel on the campus, so we have to live there. We have to live there so we can go, through, where they critique all your work for a couple weeks. So there's a beautiful pool, there's a beautiful lounge, there's a beautiful restaurant, and they serve you all your, the meals come with your tuition.
Oh,
Yeah, and the pool and everything. So we used to have we had 5 people that I've known for 3 years, and we're all at the same stage, and we would have dinner, and then we'd have a drink, then we'd go float around in the pool till 10 o'clock at night, do no homework whatsoever, and then go back the next day. And it was fun, yeah, and I felt sorry for people. I would always invite them when I would see them walking by. Hey, come hang out with us in the pool. Come have a drink with us, or come have dinner with us. I would always invite people that were wandering around by themselves. I felt sorry for them.
We're at the point where you just can't stop.
Yeah, but that's a blessing. It's a gift. Friends are a gift from God. They really are. Some friends are a gift.
It's the same thing. Okay. So I did that, and it's true.
Okay.
So how would I write that then over here?
Just yes in that area. Then a no. Put it in the slot that it belongs in. When you're putting it on top of one of the, in the middle, because that's what it represents, the area in the middle. Because if you put them on top of these little notch marks, you're going to get confused.
So that would be no.
No.
And no.
No. They alternate. No. I mean yes, no, yes, no, yes, no, yes, no. The words yes and no switch. That's what alternate means. Yes and no. Yes, no, yes, no, yes, no.
Okay.
All the way down. So basically that's why it only takes you testing one area, because then you know whether it's a yes or no in that area. That determines all the rest, right?
So how would I write that in an interval notation?
Okay, so this out here would be negative infinity.
Okay.
You're coming from negative infinity into 1.
Okay.
So negative infinity to 1 is part of the answer. That's not part of the answer. And then 2 to 3. So you would go, you write it. Let's see how you write it.
So it'd be a bracket.
Yeah, good.
And then the little u, right?
Mm-hmm.
And then,
Beautiful.
and that's it?
That's it.
Okay.
It's easy, right?
Yeah.
Easier than the rest of the chapter. Well, some of it's easy, some of it's not. You're welcome.
Bruh, those teachers love me. I'm not. Because I was like one of the only students that could actually read Spanish. All of those kids were just wasted because we can't read Spanish. I was just really What's a constant?
A number that doesn't change. It's constantly the same.
I understood that, but what does it do?
What does it do?
If it's a problem, like if it's in a problem, I don't remember like any problems about it. But like if it's in a problem, like what are you supposed to?
It's in the problem. The whole chapter about graphing a line has to do with something that's constant. You know why the shape is a line? Because the rise and the run is constantly the same. I mean, we study that like in every math class, but
Like when x is a constant, that means it's not changing.
Yes.
That's what it's saying.
Okay, but you know when we were having that test, there were like 20 questions about constants.
Yeah.
But, like,
I mean, there's other examples I could give you, but one concept that we really study in algebra is the shape of a line. If you go like this with your finger, rise and run, no matter what 2 points you rise and run for, you constantly get the same slope over and over and over again. It builds a staircase.
they didn't give us any lines. It just
Okay, well then there's also this example. How about just x equal to 3? X is constantly 3, y is not in the equation. That happens to be called a constant equation. And that would be a line that goes like this.
This is the easy stuff I got wrong.
Y equal to 3. I just put it on your last test. That's a constant equation. Y is constantly 3. X is not even in the equation. That was on your last test. This is not about that. This chapter 3 is about graphs that go like this. Nothing's constant.
I was asleep for most of
How did you not know? What is this, on the PERT?
No, the PSATs.
I hate that test. It's so hard to tutor students for that test. It's just all over the place.
Yeah, but there was like so many questions about constants.
What grade are you in? You're only 10? 10 years old? Oh, I was going to say, you're really advanced for 10. You look like you're older. You're in 10th grade and trying to get a college degree? Is your parents pressuring you to get done quickly? No? You just want to get it out of the way, get that free money, get those free classes. But then look what's going to happen. You're going to go away to school and you're going to be around all these older people all the time. Do you want that?
You never want to say
Trying to leave your mommy? My daughter left. I cried like a baby. I still call her all the time. Can you come home? She's, I'm 27, Mom. Would you leave me alone? She's like, no. All right, here I go again. Starting, so congratulate yourself. You're on the last chapter now of the book. We finished with 5 this particular class? Yes. I don't know, whatever it says on the amended schedule post-Dorian. I don't remember what it said, but maybe it says there's a test, maybe it doesn't. Why don't you look at that schedule?
So we're not having a test 4?
Oh my God, it's like I'm talking to people that have no ears.
I've seen it, but like, I don't know if we like made a mistake on it.
I mean, how hard is that to look that up online? Why do I have to put it out here for you? Let's see if there's a test. It's as easy as looking at the schedule that I posted for you. Let's see. I mean, it might have gotten canceled because of how much time we missed. Let's see. For Chapter 3, we got one for Chapter 3. This is when the actual Chapter 3 is? Yep. Next week, 11/13, right? And then I was supposed to do 4.2 and 4.3. I can't remember because I redid this so long ago. Yeah, I might have taken that baby out of there.
Which baby?
Chapter 4 test.
Oh, yeah, I think you said you did.
I think I had to because we missed so much time because of Dorian.
And it was supposed to be on the day when we like had off for Thanksgiving too.
Yeah, so then I said that wouldn't be worth it. I didn't want to stress my little babies. So, yeah. So now what will happen is instead of me having 3 tests to use and split up percentages, now instead of having 4 tests and a final, now I have 3 tests and a final, okay? Everything from Chapter 4, now everybody knows that it's cumulative, the final, right? All math classes at the college level are cumulative. Okay, let's go. 4.1. Wasting time here. Okay, get your calculator, make sure something like this, not that I would even put that on a test, but make sure that you can enter that in the calculator just in case I go soft and decide to put that on the test. Okay, so this would just be 6 raised up to, everything is exponential or logarithmic in this chapter. Exponential, logarithms are the inverse of that. So if you were pressing this in, this would just be 6 raised up to. Now, since the power is going to be an actual operation that you're going to do, you want to put it in parentheses. Square root, put an 8 in there, close it up again. Every parenthesis should have a mate. Okay, so this said approximate each number. It didn't say what to approximate to, so let's approximate to the 10th place. 158.8. Okay, go to the next page. I mean, I don't know that I needed to put these on the outline. Why don't we press something like this in? Now, you can try the 8 raised to the negative 2 without a parenthesis. See what happens. See if you get the same answer as me. I'm going to put mine in parentheses. So 8 raised up to a power of, since there's a negative there, I'm going to put it in parentheses, but see if you get the same answer without. Did you get that?
Yeah.
Okay, so now you know you can do it without. So for this problem, round to 3 decimal places, 0.010. Okay, the E, if you don't know about E, you know what pi is, right? 3.14 just runs on and on and on. E is the same kind of number. When they run on and on and on, then they're called irrational, and we always have a key on our calculator that represents them. It's in the first column. The E number is approximately 2.714, just like pi is approximately 3.14. So, and you can tell right here. Great. Awesome. All right, so here's the E key right here. So it's second E. Like if you wanted to know what this E value is, you could just put a 1 in there. See, that's how big E is. It runs on and on, but this is all that your calculator can hold. Now the problem you're doing said go E, base of E, that's the base, raised up to a power of negative 0.13. Now when you use this E key, it automatically gives you a parenthesis, so just match it. You're going out to 3 decimal places again, 0.878. Okay, I want you to know that when you're graphing, These are the kind of graphs that you're going to get. Whenever it's an exponential graph, it looks like this, but it's either going to go to the right or to the left. Okay? Here's how you know when it's going to go to the right or the left. Okay, let's say I give you something like this. If the base, this is the base right here. That's the base. If the base, A in this case, is greater than 1, it will climb like this and up to the right. These are exponential graphs. The x-axis serves as the asymptote. See how this little wing right here is hovering right above the x-axis? So this is considered the asymptote, but that's a parent graph. A parent graph will look like this. It'll be held up, this little wing right here, it'll be held up by the x-axis and it'll go right through the number 1. That's if I put no shifts on it whatsoever. These are the key characteristics of this graph. Tail hovers above the x-axis, goes off to infinity to the right when the base is greater than 1. And it goes through the number 1. The minute I start shifting it, you're going to shift that point at 0, 1. You can also shift the horizontal asymptote. If I go like this. So an example of a graph that would look like this is an equation like this. See how my base is bigger than 1? That makes it climb upward and to the right. It'll still go through 0, 1. Okay, I'll tell you why when we go to start graphing them. If I give you something like this again, only the base is less than 1. Not negative, but less, between 0 and 1. If the base, and we're calling it A, if that base is in between, bigger than 0, but less than 1. So like a fraction, 1/5, 2/3, a fraction where the top numbers, then it goes like this. Still goes through 0, 1. I don't know. Let me think about it for a minute. I guess. You're welcome. So when the base is bigger than 1, it's going to go to the right. When it's less than 1, it's going to go that way. That I will give you. An example of something like this would be 1/2 as the base raised to an exponent of x. Okay, it will either climb to the right or climb to the left, going right through 0, 1, unless I start shifting it around. Okay, so in problem number 4, what does this graph belong to? I think what you should just do is put those in your calculator until you find the one that looks like this. I mean, you could rule out some of these. Like, for instance, does this make sense to you? You guys know stuff about parabolas, don't you? And if I put a negative in front and how it flips it over, same thing here. If I was to throw a negative right out here, it would take this graph and flip it upside down. So you might be able to rule out certain graphs. So what choice is here, A through F, do you think you can rule out? B and F. B and F, cross them out. Because if that was the case, they would be flipped upside down. So that's no good, that's no good. And that's because of this. That's why we're ruling it out. Okay, then let's try and see what these do. Do you see that the shifts are in different places? Like what this says right here, this says that you're going to have a horizontal shift. See how you got a number attached to your x? You're going to have a horizontal shift of +1. This one says that this is just this one's just a basic graph. It has no shifts. This one is a vertical shift. I don't know if you see the difference here. Do you see that this is a number that's attached up where the power is to the x? That's a horizontal shift. Whereas this is not attached to the x. It's a free loose number, not added or subtracted. So this one's a vertical shift. This is one that will be higher than it typically is. Do you have any idea which one it is right now? I mean, we can go to our calculator. We're definitely going to go to our calculator. But if you had to guess, You think that it's A. All right, why don't we put that one in our calculator? See what I'm saying? That you could narrow down instead of putting all 6 of them in your calculator. You could rule out ones that don't make any sense. You know this thing is not flipped over, so we ruled out that and that. And then if you know the difference between a horizontal and a vertical shift, you can narrow your choices down even further. So let's put that one that you think it is, A, in the graphing calculator and see if it looks like what you have on your worksheet, your outline. Let's get rid of this, go into Y, get rid of what was there. We're doing 3 to the x minus 1. You got to put that power in parentheses. So it's 3 raised up to a power of, the power is this entire expression. So put it in parentheses because there's more than one term in the power. Okay, let's do graph. Whoa. To me, it looks like it's A. What other ones were we choosing between? Well, it can't be D. You could let's see what C looks like. Now look at let's get rid of now. You see how this one? I'm going to put less numbers on here. I'm going to go so you can see it more clearly. The window. It goes from -10 to 10. I'm going to make it go from -5 because if I put less numbers, it'll be clearer. Oh, actually, it was the y-axis that I wanted to do that too. But let's try it with this. Let's see what it looks like now. It'll be easier. You see how it cuts through right at 1/2? So if it was this problem right here. This one right here, 3 to the x. If it was this one, it would have went through 0, 1. Oh, they go through 0, right through 0, 1. It does not go through 0, 1. See, it missed it. So you can cross that one off also. When there's no shifts whatsoever, it will go through 0, 1. Because this is bigger than 1, it had to climb to the right. But it missed the mark right there. That's why I can just cross that off. So I'm not even going to bother trying that. This is a vertical shift of, it should be 1 lower, so it can't be that. So it has to be that. It has to be this one. Put this one in just so you can see what it looks like. That makes it twirl around the y-axis. So just so you can take a look at it, let's look at it. All right, so this is the one you think it is, and this was the other one that I just wanted you to put in there. So 3 raised up to a power of -x. There's where you get the x's. It's going to graph this one first, then this one. Huh?
The negative x one makes it like upside down. Like it starts on.
Yeah, it flips it over. Okay, look, there's the first one. There's the second one. So basically what it did, it spun across the y-axis. It took the one that was like this and flipped it across the y-axis. That's always what happens when you put a negative in front of your x. All right, so moving on. So the answer is A there. Okay, moving on to this. Let's do a graph of this. This says do transformations. So here we go. This is the first one. You got to give me 2 graphs when it says transformations, unfortunately. Let me show you how to do some basic arithmetic with this. This is going to be my parent graph. This is going to be my transformed graph. I'm going to try not to do much work for the transformed graph. Okay, here we go. I think you should plug in 0. I think you should plug in a negative. And I think you should plug in its positive counterpart. Okay, over here you can do the work. You're only plugging in right here. Now, do you know what any number to the 0 power is? If you don't, please put it in your calculator. What do you get when you raise 5 to the 0? 5 raised up to the 0. 1. Anything to the 0 power, and if you don't know that, just use your calculator. We're going to plot points here. We already know what the shape is supposed to be, so you're going to get yourself a few points, and make the shape. Okay, this one, I don't know if you know what that is. Please put that in your calculator. It's 0.20. Please put, oh, if you don't know how to put it in your, well, how could you not? Just 5 raised to the negative 1. What do you get? Make sure you're getting a point 2. Everybody get that? Yes? You didn't try. Okay, then how about this one? 5 to the 1. What's that equal to? 5. Anything to the first power is 5. Go plot the points. Remember what the shape is, because you don't want to try and connect the dots in some crazy looking shape. So 0, 1 is right there. Then negative 1.2, negative 1, tiny bit above the x-axis. 0.2 is not very high in the air. And then 1.5, here it is, going off into infinity. Remember that the tail hovers above the x-axis and then off to infinity. Okay, now you're going to get the transform graph, but you're going to try not to do much work. What kind of shift is this? Horizontal or vertical? Okay, what does vertical mean? Does it mean that the y coordinate is changing, or does it mean the x-axis, the x value is changing? Y's, right? Vertical means up and down. Your y coordinate is your up and down coordinate. So why don't we build off of the table we already made? We already made a table with some nice values. Let's just change the y values. Now with vertical shifting, you do not switch the sign. We are actually going to use a -4 on each of the y values we already knew about. We will not be changing the x values. So 0, -1 and 1. I taught you this in Chapter 2. Be able to read the shifting whenever you're doing a transformation. And we're changing the y value. So you look at what the y value used to be. I'll put it right here. And then you subtract 4. So it's -3. Look at what it used to be. Subtract 4. So that would be what? 3 point what? Or -3 point what? 3.8. Good. And then you look at what it used to be. It used to be 5. I'm taking away 4. I'm using the values that were on my parent graph. And this is 1. Now go plot that, and you'll have a transformation. You'll have the original graph as well as the vertically shifted graph. All the points are going to be 4 units lower. So when I'm at 0, instead of being at 1, I'm 4 units lower than that. Right there. See? 1, 2, 3, 4. Right underneath that point that it went with. Then at -1, I'm going to be down at -3.8, so approximately right there. Now, you got to keep in mind what the shape is, because no matter where the dots are, you want to connect them in the shape that you've memorized. Okay, exponential graphs look like this. They climb up to the right and to infinity when the base is greater than 1, as this is. See that 5? It's greater than 1, so it has to climb like this. Last point, 1, 1. So 1, 1 would be right there. Give it the same shape as this. Okay, let me tell you, let's talk about the plate, the shelf that's going to hold up that tail. The x-axis, isn't that holding up this tail right here? We need a shelf right here that is going to hold up the new one. Did I say that this graph was 4 units lower? That means the asymptote too. Not just the point. It's not just the points that are 4 units lower. It's this asymptote also goes 4 units lower. So instead of it being at 0, it's going to be down here. That's the shelf that's going to hold up this tail. And when you go doing your graphs for me, I need to see that you understand that the asymptote moves just like the points move. Okay, transformations. Okay, let's do it one more time. I want you to try and use your head and do it yourself. I know, use your brain. Oh my God, how can I possibly do that? I don't have a brain. I'll do the parent graph for you, and then I want you to do this, and I want you to graph both of them right here. Go ahead. Let's do this first. Pretend as though this is the graph. Y is equal to, that's the same thing as h of x, but instead of all this nonsense that's here, where you have a 4 added to the x and then an extra 5, let's just pretend it's just 4 to the x, with no extra junk right here, no extra junk right here. This will be our parent graph. Again, I suggest you try easy numbers like 0, 1, and negative 1. Okay, again, I'll put the work out here. And then we'll put the transformed table right here, where we're using all of the stuff that they gave us. All right, so anyway, if I was plugging right into this parent graph, I would be doing 4 raised up to the 0, that's 1. I would be doing 4 raised up to the 1, that's 4. And I would be doing 4 raised up to the negative 1. That you might want to put in your calculator. It's 0.25. Can you two stop? I can't concentrate because I keep looking at you constantly having a conversation. Please stop. Okay, so we're going to do this for our parent graph. Let's do this for the transformation. Try to read off of this thing. What do you think as I go and fill in the numbers? I don't want to plug in anymore. I don't want to plug in. What is being done to the x values? Because we could use these x values, and if you could read what that new function is telling you to do, then maybe we could just do addition and subtraction to get all the answers instead of raising to a power. What is it? Subtract 4, right? Isn't that a horizontal shift when it's attached to the x? So maybe label that you are really going to subtract 4. You're not going to add 4, you're going to subtract 4 because this is a horizontal shift. You can tell because it's attached to the x. So what you're going to do is you're going to take these values that you just had in your nice pretty table and subtract 4. Then you don't have to bother yourself with raising to a power, which is a harder operation to do. Anybody can subtract in their head. So you'll go 0, take away 4, because you're supposed to be horizontally shifting all the x values. You'll go 1 minus 4. You'll go negative 1 minus 4. And get all the values, but without really plugging into the function. That's what transformations are about, that you play off the parent table. Okay, this is what kind of shift, vertical or horizontal? It's got to be vertical because we already talked about that this 4 is a horizontal. Vertical shifts, they behave exactly like what you're looking at. And you use them on the y-coordinate. When you're talking about a vertical shift, you're talking about changing your y values. So you're going to look at the y values that are on the table and add 5. So 1 plus 5, 6. 4 plus 5, 9. This plus 5, 5.25. Now go plot both of them. Okay, so 0, 1 would be right there. I'm doing the original one first. 1, 4, bless you, right there. And then I'm doing negative 1 with a teeny tiny y value right there. So this is your original graph going to infinity, but having a tail that hovers above the x-axis. That's the original one. Transformed one is negative 4, but you're going up to positive 6 right there. Let's see, what else? Negative 3, 9. To get this mark out of here. Negative 4 and up at 6, 7, 8. Okay, so negative 3, 9. So negative 3 be up here, about right there. And then negative 5, 5.25. Negative 5, 5.25. So this would be 5, tiny little hair above the 5 mark. This is your new horizontal asymptote. Whereas this used to be your horizontal asymptote. So you go like this. Let that tail hover above the new horizontal asymptote and up to infinity. Those are your two graphs. When I ask for transformations, you're going to give me both graphs, the original and transformed one. Okay, enough of that. Let's go to, see what else is there. So I did 2 transformations. But, you know, I will tell... Oh, well, they tell you what to do. They tell you to make one table like this and then one table like this. and you could just do the tables from scratch if you want. This is saying take your x values and multiply them by -1 on the new table. But I already did 2 of those, so here we go with this one. This you got to use your calculator for. All right, so let's do one more of these. How about if I do the harder one? Because these are both have to do with an E graph. I'm going to do the one that has more things to do. All right, let's do the original. Now, if anybody in here is paying attention, I want you to tell me, what should my first baby table look like? It should be based off of what equation? Not this one. And doesn't it say it right up there in the first sentence? That's your baby stripped down equation? It says it right there. It's the way the equation looked before they started subtracting and adding. It's not that hard to understand. So it's just e to the x. Okay, this number right here, it is bigger than 1. E is 2.7. So it is going to climb to the right. I already know that. I'm going to make a little table. But since the base is a decimal, I'm going to have to use my calculator to assist me with the table. Once I get done with the table, look what we're going to do for the other one. Let's make a plan. So we're going to do a table off of this one. We'll only do 3 values. We don't really need to do more than that. Then we're going to try and deal with this one right here. I don't know why I'm writing it twice. It's right above where I'm doing the work. So why don't we just jump into talking about the plan? What do you think this equation is telling you to do to your x's? Is it telling you to add 5 or subtract 5? Okay, so why don't we put that as our plan? Because we'll do this little baby table, parent graph, and then we'll just take all the x's and add 5. What is this equation, this transformed equation, telling you to do to your y's? Add 3 or subtract 3? Subtract 3, because you got to remember that when it's attached to the x, it's a horizontal shift. You must switch it before you actually use it. So that's why I switched that one, but you don't ever see me switching this one. So if there's a -3 there for my vertical shift, I don't switch it. I just actually use it on the y's. You use the vertical shifters on the y's, and you use the horizontal shifters on the x's. Okay, so let's go. We're going to do a transform table and a baby table. The baby table is what's called the parent graph. All right. So first I'm going to use 0. I like these numbers just because they're easy. Now you are going to have to use a calculator. Anything to the 0 power is 1. But if you need to enter that, enter that. E to the 1, well, if you know what E is, then E to the 1 is 2.7. 2.71. I'm just going to put 2.7. I don't need to go crazier than that. This you better put in your calculator. Go put that in your calculator and tell me what e to the -1 is. 0.367? Okay, how about 0.3? 0.37. 0.37, I'll use that. That's a nice approximation. All right, now here we go with our shifting knowledge. That hopefully you have acquired some kind of shifting knowledge because I did it in chapters 2, 3, and 4. All right, so you're going to take your x's, do one column at a time. Don't go back and forth, you'll get confused. Take all your x values that you have right here, add 5. See, you don't really need to plug into the function. That's too much work. Know how to shift. I'm going to do this first on my x's. So I'm going to go 0 plus 5, 5. 1 plus 5, 6. -1 plus... Oh! My God, are you serious? That scared the heck out of me. I was ready to get everybody get under the desk. I'll pull out my piece. What the heck? That scared me. Don't mess around with me like that. No, I don't know him. -1, let me see, -1 plus 5. I was going to throw this thing. Play around, man. Campus destruction. Okay, so anyway, -3. Now you're going to take the y's and subtract 3. All right, so now just look at all the y's and subtract 3. Do it in your calculator if you have to. So 1 take away 3, negative 2. 2.7 take away 3 is negative 0.3. And then, let's see, 0.37 take away 3. You're going to have to put these in your calculator if you don't know what they are. So let's see, this would be negative 2.63. Yeah, thank you. Negative 2.63. Okay, let's plot these. We're going to do the baby shape first. Remember, follow the same shape on both of them. Okay, so 0, 1. Then we're going to do 1, 2.7, almost at the 3. So right there, it's starting to climb upward. And then negative 1 and a teeny tiny hair above the x-axis. So if you know the shape, you don't have to do more than 3 points. You see, it's getting very close to the x-axis. That's the hovering part, where it's got the horizontal and vertical shifts all built into the table. So now we're going to go 5, negative 2. Then we're going to go 6, and then we're going to go negative 0.3. So let's see, I'm going down. That's a teeny tiny bit above there. Then, let's see, then it's 4. That makes no sense. Did I do that right? Somebody put in your calculator 2.7 minus 3. You got negative 0.3? Okay, just checking. Okay, so blah, 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 blah. Okay, 2.7. I don't know why I'm getting a brain fart here. Okay, so this is over 6 and right there. All right, then 4 and negative, what is it, negative 2.3? So 1, 2, be about right there. So this is going to be like this. Whoops, missed. Why are you constantly laughing? Okay, one more and then I'm done with this. I'm tired of this section. Oh, I got to do one of those too. So I wanted to give you a graph where you're going the other way. So I chose one of these where there's a base of 1/2. The minute that the base is between 0 and 1, instead of it climbing to the right, it's going to climb to the left. But the numbers in the table will tell you, it would be nice if you knew that so that you wouldn't be thinking you did the calculations wrong. Okay, so let's see. Let's do the parent graph first. The base is in between 0 and 1, so the calculations might be harder for you. I don't know. Let's try the easy numbers that I keep trying just because it makes it easy. I'm going to do the calculations for you right here, but you can do it in your calculator. So it's 1/2, or anything to the 0 power is 1. Then the next thing I would be doing is going 1/2 again, but this time to a power of 1. I mean, that's just so easy if you use 0 and 1 as your first two x values. And then this one, I don't know if you know this one. When you take anything and raise it to a negative power, look what happens, because you might prefer to do this by hand. All it does is take what's right here, the base, it flips it over, and then the power becomes positive. I don't know if you remember that from algebra or not. This is the same thing as this. Flip over the base, the power becomes 1. 2 to the 1, 2. So you can do these things without your calculator. It's harder to put them in the calculator. I'm going to go graph this. I'm going to go 0, 1. Now remember, this thing's going to go to the left, not the right this time, but it still has that same cut-through point of 0, 1. 1, 1/2, right there. Tiny little hair above the x-axis. Negative 1, 2. See, it's starting to climb higher and higher now. Negative 1, you're up at 2. It's just going in the opposite direction now. The tail flutters above the x-axis. Now do the shifted one. Okay, let's try to do what I told you with shifting. Plug in all over again. You can still use this table, but do these things. Now let's see if you got this. Let's see how bad your brain cells have gone. Should I add to the X or subtract? Add. Okay. Are everybody looking at this number right here? Forget this. Forget this right now. I can only handle these two right now. I'm just looking at those two. Anyway, I'm looking at that, right? And you're adding 2 to the X. So go and take the X values that we so nicely got together and add 2. Okay, forget that. It's too much. All right, so it's 2. And then it's 1 and add 2, 3. And then it's -1 and add 2, 1. Now take these numbers and what should I do to those numbers so that I don't actually have to plug in? What should I do to them? You're gone, man. Something happened to you. You got like the doe in the headlights look right now. What should I do to these y values? So says that transformed equation. Add 5. Those of you that have a blank look in your face, you better just take a nap. You're done. All right, you're going to go right here. That's your vertical shift. Vertical shift, I've only done 17 problems like this tonight. That is something to do with the y's, and you don't switch it. So you should be adding 5. This was the horizontal shift. They always get switched. Repeating thing in many chapters. So the y values are 1 plus 5, 6. 1/2 plus 0.5, 5.5. And then 2 plus 5, 7. Okay, go graph this. It should go in the same shape. It's just shifted over. It's got a horizontal shift and a vertical shift, which is built right into your table now. It should have the same shape, same direction. All right, so if I go 2, 6, right up here. 2, 6 is right there. Then if I go 3, 5.5, I could go, let's see, 3, and be a little bit underneath that, so like right there. Almost the same height. This is up at 6. I should make these smaller. Not that it matters. This. So I went to 2, then I went to 3, and then I'm going to go to 1, but I'm going to shoot up to 7. Anyway, do you see that it's starting to make its ascent upward? So go with it. That's just like the turning point where it starts to climb upward. And the tail is going to be right there. Okay, a lot of shifting in this particular section. Do you want to ask me anything? There is one banking problem that has to do with exponential and logarithm. I'm going to demonstrate that for you. All right. So when you are in, some of the classes that you took before you came here, you guys have heard of interest, right? Interest is equal to P times R times T. That's called simple interest. Then there is compounded interest. And compounded interest, you have to know how many times is the bank going to go into your account and pay you for leaving your money in the bank. Because they take your money and they make loans for other people. So they pay you for being a customer. So that's what interest is. Now, sometimes this doesn't happen in many banks. I don't know if it exists at all anymore. We have what's called, this is a compound interest formula. And then see this one right here? Label it. This is called the continuous interest formula, as though you were getting interest every moment of every day. When you're getting compounded interest, someone has to tell you when you open up the account, how often are you going to get interest? Are you going to be paid once a year? That's really like simple interest. Are you going to be paid every month? So is the bank going to come in monthly and pay you 12 times a year for the privilege of having your money in their bank? Are they going to come semi-annually? Yeah, there's not that many that give you repeated interest. You see how it is. You put your money in the bank if you're saving at this point. I don't know if you are or not, but probably not. When you put your money in the bank, most of the times you'll be lucky if they go in there once a year. But if you are one of the big hitters at the bank, you're one of these people that invests a lot of money, you're the ones that are game for multiple interest periods. That's called compound interest, where they go in more often than one time and they pay you. That's like people that they put CDs, they invest in CDs. Have you ever heard of those? Where you don't get to take it out. It's like locked there for about 5 years, and in those kind of things, they tend to pay interest more than once. So you're going to see me do one of these. Once you see the word continuous, where they imply in the problem that you're continually earning interest, you're going to switch to this formula. Please label it. One's called the compound interest formula, where you're getting compound interest. This is actually a compound interest formula also, but you're getting compound interest at certain intervals. And I'll demonstrate that for you. This, on the other hand, is called continuous compound interest. All right, so here we go. Find the accumulated value of $20,000. Let's move these numbers down here. $20,000, time is 4 years. And point out what everything stands for. Do you see that there's R's and N's and T's? This is T, the 4 years that they're talking about. See that P right there, that big P? That's this right here. It's the original amount of the principal. It's the original amount that your account starts with. Then you see the N there? So I already said what T stands for. I already said what P stands for. A is the final amount that ends up in your account after they slap on some interest. So this N is the number of compound periods. So if somebody says, we're going to pay you monthly, the number of compounding period is how many times they're going to pay you within a year. N would be 12. If they say semi-annually, do you know what semi-annually means? How many times a year? So N would be 2. If they say weekly, do you know how many weeks are in a year? 52. Then N would be 52. So they're going to use certain words that are going to apply how often they're going to pay you. How about quarterly? Quarterly is every 3 months, but how many times a year in it if it is every 3 months? 4 times, right? Aren't there 4 quarters in a dollar? Quarter means 4 times a year. Okay, so look for certain words so that you can do the problem. So N is the number of compounding periods per year. Number of compounding periods. How often you're going to be paid per year? Periods per year. Okay, and this, where do they say? Let's do A. Let's do part A. So it's going to be semi-annually. So does everybody understand for semi-annually you're getting paid twice a year? When you go to do part B, it'll be N is equal to 4. So this is what I'm going to do. I'm going to do part A, part B, and part D. Okay, here's part A. I'm going to write the formula for you so you can watch me plug into it, and you got to be careful when you plug into it. Okay, there's the formula so you can kind of eyeball it. The P, $20,000. We're looking for the final amount in the account. Then it's 1 plus the rate. What is my rate here? Do you see that it says 5% right there in the problem? So you have to put the rate as a decimal, though. Maybe you can write that right here, that the rate was, they said in the problem, was 5%. P is 20,000. Time is 4 years. But you're not ever allowed to use it in any of your formulas. You don't use it as the percent. You slide the decimal over 2 places to the left. So you have to use it in this form right here, 0.05, if you have forgotten that. Okay, so now come back over here. I'm doing rate as a 0.05. Number of compounding periods, because they use the word semi-annually. Probably spelled that wrong. So twice, that goes there. And then up here as the power, again, it's the n value, which was this right here. Use it here and here, times the total amount of time. Now, I would not put all that in your calculator. I would try to do some of it in your head. Why don't you go 0.05 divided by 2? For what? How much? It's 200,000? Oh. Thanks. Okay, so 20,000. Somebody go 0.05 divided by 2 unless you already know what it is. What is it? 0.025? So why don't we just call this 0.025? 1 plus 0.025. So 1.025, because that'll be a lot easier. And then, of course, do that in your head. Now put it in the calculator. Because if you're going to put it in like that, it's kind of messy, but go for it if you want to. This is what you should be getting as your answer. All right, so let's see. Clear, clear, clear. We're going to do 20 times 1.025 raised up to a power of 8. Okay, so now I got that he had 24,000, but after 4 years at the given information, he ends up with $24,368.06. So 24,368, and go out to the dollars and cents, hundredths place. Hey, I wish I had time actually to do B as well, but I don't. I'll just set it up and then you can press it in your calculator. This would be part B. Now we're going quarterly. So it's A, I'm following this formula, 20,000 times 1 plus the rate, which was 0.05, but this time quarterly, n value is 4, and then I'm using a power, sorry, I got to slip this down here, well, I'll put it up here. My n value was 4 times 4, because the t, you got to put t for 4 years, and the n was also 4. Can somebody put 0.005 divided by 4 in the calculator just so I can clean this up a little bit? 0.0125. Thank you. And we're going to have a power of 16 this time. So you see all that's changing is your power and the number that's in here. Times 20,000. Pop all that into the calculator. So it would be 20. I'm going to try it without the parentheses. Times, because I think it'll work, 1.0125, raise it up to the 16th power. Did you get that? 24397? Okay, so 24397 and 79 cents. Okay, last one I'm going to do from this section is part D. Hello. Okay, so part D. Now they use this word. The bank is paying you continuously. At every moment you're earning interest. So now once you see the word continuously, you are to switch formulas. So it's P. This is up in the directions of the problem. P is equal to, or amount is equal to P times E to the RT. You no longer have the N value anymore. Compounding periods, because you're being paid continuously. So this is actually less work. So it's 20,000 times E to a power of R times T. So you can put it in the calculator the way it is, or all right, so here we go. For this one, it was 20,000 out front, times E, second function E, that's what you're multiplying it by, and then inside the power put 0.05 times 4. You should have gotten 24,428. The best kind of interest you're going to earn, that you're going to end up with the most money, is this continuing interest. 06 cents? Hey, there's my work for that. That completes section 4.1. Okay, now I know that you can't bear to go on, but what do you want me to do? I mean, I think I can, here's a plan that I think maybe might work. I was 4.2 tonight, 4.3 next time I see you. I'll give you the review if you want, but then you're going to have to pay the price by me possibly having to teach one of these sections in chapter 4 by video. Because we only have one class after this next test, I think. And how am I going to teach 3 sections in one class? You see, I can't do that. It's impossible. So let's do as much as we can. I'll give you the review. Do not count on my review. You're asking for trouble if you do that. If all you're going to do is come and watch me, let's just take a paper and put a D on it, a D or an F. That's what's going to happen to you. Okay? If you're going to at least do it once or twice, once at home, and then I'm your backup, oh, then that might work. And that's if you're pretty skilled. If you know that you've been doing terrible, this is your last shot. You should do it twice at home. If you have failed both tests, that means you have no study skills whatsoever. You're probably not even studying. Come back to college when you're more mentally prepared to handle it. That's what I think you should do. Otherwise, do what I'm saying right now. If you have not been using the practice test, do it like twice, and then I'll just be one that refreshes you on the night of the test. Because I cannot save you and make you remember everything in 45 minutes. That's not going to happen. So don't count on me for everything. Okay, let's go to 4.2. Oh my God, where did the worksheet go? I'm brain dead, and now I still got to teach trig. Okay, we are going to go now to the inverse of exponents, the opposite of exponents. You know how this had like a little tail that hovered above the x-axis? Well, now the tail is going to hover alongside the y-axis when we do go graphing it. First, I got to get you to learn the mechanics of how to rewrite a log, because you're going to see, I'm going to start asking you to evaluate the log of certain numbers. You won't be able to do it. You can't do logs in your head, but you can do this. Learn how to rewrite them in exponential form, then you'll be able to handle them. So the whole key in this section is learn how to go from log form to exponential form and vice versa. This is the one that you're really going to want to go in as you do the majority of the problems in the section, but they do start off by telling you to go forwards and backwards. So you can look at the definition at the top if you want, but I can explain it a little bit easier. When you're trying to go from this form to this form, let's look at the mechanics of what happens. You see that there's a little subscript hanging off of the G right here, right? You're going to push that up, and I mean, it's called the base when it's in this form. This is read like this: log of x base 7 is equal to 3. So this thing that's called a base when it's in log form and hangs down below the G, it's still called the base even when you put it in this form. You're more familiar with this form. Isn't that called the base, the 7? It's called the base here too. Only here it hangs down, and then here it's up, you know, it's a little higher. As far as the other things, when you go from this form to this form, you see that the word log disappears, right? You're going to get rid of the word log. You're going to push this up, and you're going to grab as its power this thing that's over here by itself. So in other words, these two are going to round robin. This is going to come here. This is going to take its place. But the 3 is going to come over here as a power. Let's practice doing that. Okay, watch. Okay, put an equal sign. This is how you have to train yourself to do it. If you're going to go from log form to exponential form, the word log has to be gone. Okay, so that's a given. You cannot have the word log now. All you're going to do to get this to happen is, see this? Push it up. I don't care where you put the 7. Put it on the left or the right. It doesn't matter. But don't let it hang down like that. Push it like this. Put it level with the equal sign. And then switch the remaining items. There's only 2 things that remain. I've already dealt with this guy. I pushed them up. Now switch the only 2 things that are left, the x and the 3. Forget about the word log because you're trying to go from log form to non-log form. So the x is going to be over by itself. The 3 will no longer be by itself. X is going to be by itself. 3 will no longer be by itself, and it's going to jump into the exponential position. Let's do the same thing with the next one. You're going to push up the b. You must have an equal sign. Now switch the remaining 2 items. The 25, instead of being with other things on the same side, it's going to be by itself. The 2 is going to come and be with some of the items that were in the problem. Okay, so 25. Why don't you write the thing that's by itself first? Then there's only one number, and it has to be the power. The only thing I haven't used is this 2. Goes right there. Okay, likewise for this next one. Push that 4 up. You should go in the exact order that I'm doing it because it'll be the easiest to remember. Put your equal sign. Push the 4 up. It's going to be the base. Now get those other 2 things in the right place. Okay, there's only these 2 things that are left. I already wrote the 4. And you know I don't want the word log. There's only 2 things left. This thing that's by itself will no longer be by itself. It'll be with other things. This will be by itself because it's going to go over and take its place. Okay, so the 26 will be right there, and the y will be right there. So that's how to go from log form to exponential form. These are all called exponential form because you don't have the word log anymore. You got to be real good at this in this chapter. You're going to practice this throughout the whole section. Okay, let's say I started you with that right there. Why don't you try? You should even try to cover them up yourself to see if you can write them yourself. Okay, let's say you were trying to get into log form. Then just write the word log. Put an equal sign. See that 2 that's a base? Isn't it still going to be the base when you put it in log form? Only now it'll hang down here. Okay, then once I've written the word log and used the 2, I will cross off the 2 so you don't use it anymore. You only have 2 more numbers to get in the proper place. The 5, or 2 more expressions, the 5 and the x. Okay, see if the x was alone, it's not going to be alone anymore. This is going to come take its place. There's always the remaining 2 numbers always switch sides. Okay, the 5 is going to go out and be by itself. I like to write that one as my next number because then there's only one thing left, the x. That'll go right here. That 3rd piece doesn't become the power. It's right in its level with the word log, right on the same level. Okay, let's do it again for the next one. Put log, put equal. If b is the base here, it's also going to be the base here. It's just going to hang down off of the g. So I always put that in place first. Then I need to fill in that spot right there and this spot. So look at what you got here. 27 was by itself. That'll no longer be. I've already mentioned the b. I'm not messing with that. I just want to figure out where to put the 3, where to put the 27. The 3 is going to go over and be by itself. The 27 is going to take its place. Okay, 3 is going to be by itself. If you put that one next, it'll help you to get the 3rd one right. And the 27 will be right here, level with the word log. It'll be right out in front of the word log. Okay, one more. Okay, there's 2 kind of logs. There's log base 10, and there's kind of log as a base. Log that has this as a base is called natural log, LN instead of LOG. So I'm going to go LN, put put my equal sign. This base right here will still be the base. When the base is e, it's a natural log. I'm done mentioning that, so now you got to get the y and the 33 in the right place. So the y is going to go off and be by itself, and the 33 will be right out in front of the log. Only it's a natural log this time. So that's going forwards and backwards. The reason that you're learning how to do this is so that you can solve logarithmic equations. Yes, what's your question? Oh, what? Go ahead. I didn't know. He was raising his. What?
Oh, okay. On the paper, it still says log right there, so you're going to count that.
You could actually give it both ways. My math lab will take it both ways. But really, that is what ln means. I'll take it both ways also. You're thinking about solving equations, and your teacher has probably told you because you had to have seen this before. If you took Algebra 1 and Algebra 2, they put in both classes in high school, that when you're solving equations, if it just says ln, automatically the base is e. So you don't have to write it. You don't have to write it if you don't want to. Because it's taken for, it's just like if you write x, it's taken for granted that there's a 1 in front of it if there's no number, right? If you write ln, automatically it is taken for granted that the base is e. So it's your option as to whether you want to write the e or not. Okay, so let's start doing the actual problems that go with this. All right, ready? Okay, here we go. Writing it in exponential form. What number am I going to push up here? The 5. So it's going to be 5. Put the equal sign in. It'll help you get focused and clear. We already did that. We know we're not going to mention that. So that means we just have to figure out where the 4 and where the 625 goes. Okay, 4 is the power. Now, however you rewrite this, it should be a true statement when you get done rewriting it. Okay, so the 4 becomes right here. And if you were to put this in your calculator, 5 to the 4th is 625. You should be able to verify what you're writing. Okay, same thing here. This one, I don't know if you could verify it, but you probably will be. We're going to raise this thing up. We're going to put the equal sign. We're done stating this. We're not going to state log because we're trying to go into exponential form. The 2's by itself. We got to switch these sides. The 81 needs to be by itself like the 2 used to be. And the square goes right there. See, you haven't seen this yet because we haven't gotten far enough. You're learning how to rewrite without logs so that you can solve equations like that. Because if somebody was to tell you to solve this, you wouldn't be able to solve it the way it is. But the minute that I put it like that, what does B have to be? It becomes easy all of a sudden. It has to be a 9. B has to be 9. It's the only thing, well, it could be 9 or negative 9, but it is said that when you're doing logs, the base has to be positive. That's why you wouldn't give the negative answer. Okay, so let's keep going here. Rewriting this, push the 3 up, put the equal sign right away. You're not going to say that. You're done saying that. You just have to switch these two. The 81 is going to go and be where the y used to be, all by itself. The y becomes the power, or the exponent as it's called. Okay, go back the other way. You're already in exponent form. You want to go to where you have the word log in your problem. If you're going to have the word log, write the word log, write an equal sign. What hangs down off the G? Which of these numbers hangs down off the G? See, if you put that first, it'll help you to figure out where the other 2 go. Okay, we already said the 3. We got the word log. We just have to figure out where the 2 and the 9 goes. If the 9 used to be by itself, the 2 should now be by itself. Therefore, there's only one number left. Now, you're not going to be able to verify that. You can verify when you go from log to exponent, but you will not be able to verify when you go into log form because you can't do logs in your head. What? No. No. No, there's only one and only one place for each of these. You can flip-flop the sides if you want. You could rewrite this would be the same thing as this. Okay, just as long as you have the 9 with the 3 right by the log. I don't care which one of those you give. All right, let's go to this page right here. Hang in there. I know you're squirming. So am I, but you know what can I do? Okay, so we're going to put log. Put the equal sign. That'll help you get focus on a left and a right side. What number should I hang right off of here? The 5. So put the 5 there. Then keep in mind you got to fill in a number right here and a number right there. So let's see, I'm done mentioning that one. This was by itself. So now I'll put it right here. The -4 wasn't by itself. It'll be the number that's by itself because you're switching these two things, this fraction with that. Okay, if you don't understand this, I don't know how good you are at this, but when you want to, you need an exponent or you're not going to be able to go into log form. This is the same thing as 125. You have one of these underneath the radical and the index goes right there. So your power is 1/3. This is equal to 5. Equal 5. If you want to put it in log form, you're going to have to fill out a number there, a number here, and a number here. Okay, I think I've gotten my point across that whatever the base is, it's still the base. Okay, once you get done mentioning that, you decide which guy needs to be by itself. The 5 used to be by itself. It's no longer going to be by itself. This is going to take its place, the 1/3 being by itself, and the 5 is going to come right up against the log. Write the following equation in logarithmic form. Put the log right here. Fill out that spot, and this one. Okay, so let's see. Hang that base. Switch these two. So x comes up here, 3 comes up by itself. Okay, enough of those. All right, I don't know how quick I could give you these, but I'm going to try. I'm sorry I got to keep you to the last minute, but it's almost over. Because if I have more than this to do, I don't know what the heck is going to happen. Okay, so anyway. All right, so there's this power. This you're going to use. I take you further into the logarithmic equations where you're solving. Whenever this is called the augment. By the way, these both have to be positive. Whenever this matches this, they cancel each other. They take the word log with them. And whatever the power is right here, that's what this is equal to. We're going to use, that's called the inverse property. Whatever this power is right here, and since there's no power there, it has to be a 1. So what I'm saying is this. What if I was to give you this? Log of 3, base 3 with a 2 right there. If this augment, this is called the augment, matches the base, they cancel, they take whatever kind of log is out in front, and it is equal to, this whole mess right here is equal to whatever's in the power position. If you have log of base 1, you're going to see that no matter what the base is, log of base 1 is always 0. These are things that you can use to simplify expressions, these properties. Okay, the base, these bases here, both of them have to be greater than 0. They have to be positive. If it's given to you like this is another form of the inverse property. As long as this matches this, they take each other out with the log, and whatever is the augment, that's what it's equal to. Okay, so like for instance, how do you use what I just gave you? How do you get the numbers to match? Like for instance, couldn't you write this one like this? You could go 36 is 6 squared. Isn't that 36? And then you had a hanging base of 6. Do you see how I just got this to match that? So what's this equal to? 6 or 2? 2. When these match, they cancel each other, so they're gone. It can't be the answer. And they take the word log with them, so that's 2. Okay, same thing here. If you see that there's a 2 hanging here and somebody's asking you to evaluate and you can't give a decimal or use your calculator, that means you need to write the 128 as some power of 2. You want the number that's right here. You're going to have a number to a power. You want the number that's the base to match that. So that gives you the clue. Get in your calculator and see 2 to the 5th, 2 to the 6th, 2 to the 7th. See which of those is 128. 6? Okay, so he says that I rewrite this as 2 to the 6th, so it's log of 2 to the 6th. That's my 128 with a hanging base of 2. And as long as you can get the augment and this to match, they cancel. They take the word log with them. Final answer, 6. Now, you know why I'm showing you this? By the way, just in case you don't know this, your calculator doesn't do base 2. It does no base other than 10. You wouldn't be able to do it on your calculator anyway. It doesn't do it does base 10. Whenever you hit the log key, your calculator has programmed in base 10. If you hit the ln key, it's base E. That's why you got to know how to do these properties. Okay, here we go for this one. In case you're not creative, I want to rewrite 1/8, but using a base of 8. Here's how you write 1/8. 8 to the negative 1. That's the same thing as 1 over 8. This takes this out, takes the log, negative 1. Whoa, did I finish the whole thing? Oh, what happened? Okay, so I will see. I don't know what's going to happen on the night of the test because I feel bad about this thing that I didn't finish 4-3. I'm going to review with you. I'm not going to relinquish on that promise, but try to come a little bit early if you possibly can. I don't know if you can or not because I want to start right away. Because if we have any, I'm just talking like 10 minutes, like 10 minutes. If we have any time left over whatsoever, I'm going to do a little bit of 4-3. We'll see. Okay, bye-bye. Have a good week. Love you.